This video is for topic number 9, solving absolute value equations. We're going to work on solving absolute value equations and look to verify those solutions with a graphical approach. Okay, so how do we solve an absolute value equation? Well, back when we learned about the idea of absolute value, way back in the day, we learned that the absolute value, the idea, is a number's distance from 0. Okay, so when you first learned this, they said that the absolute value of 6 was equal to 6, but they also told you that the absolute value of negative 6 was also equal to 6. So very visually, we can count out from 6 and from negative 6 and say, hey, those are 6 paces from 0. This approach will help us as we look to solve the equations algebraically, but I'd like to actually start by looking at what it means to solve an equation graphically. Well, we also remember in Algebra 1 when we did systems of equations, we were looking for the intersection of two lines. Well, we can apply the same idea to absolute values by looking to find when the solutions, or really when the x-intercepts or the zeros, occur on an absolute value. So when we look at this first example, f of x equals 3/2 times absolute value of x minus 1 minus 3. This really just means y is equal to. Well, when we find an x-intercept, what we're actually doing is we're saying, where does this equation equal 0? Or where does it hit the x-intercept or the x-axis? Well, looking at this, we see that it intersects at 2 locations. And we can label those points -1, 0, 3, 0. If we looked at a different absolute value graph, same idea. Where does y equal -2 absolute value of x plus 2? Where does that equal 0? Where is that an x-intercept? Well, we see that it occurs at 1 location. That intersection between the x-axis and the graph is only once, as opposed to here where we had it at 2 locations. And lastly, if we were looking for where does this function y equals 1/2 absolute value of x plus 1 plus 2, where does that equal 0? We see that it does not intersect the x-axis at all, giving us no solutions. Okay, so this idea of looking at the graphs and seeing where it equals the x-axis is very helpful, because when we look to solve an equation algebraically, we can actually interpret the equation not as just something that we need to do algebra on, but we can actually take this equation and split it into 2 pieces. We can look at the left-hand side and the right-hand side as 2 separate graphs. So we can graph y equals the absolute value, y equals 3 times the absolute value of x minus 2 minus 4, and we could graph the line y is equal to -1 and find where they intersect. Pretty powerful idea if you think about it, taking an equation that we normally just distributive property, combine like terms, all that stuff we learned in Algebra 1, we can take this idea and think about it as 2 different graphs and find their intersection point. So let's start off by graphing our absolute value. We remember that we're actually going to start here at hk, which is going to be 2, -4, 2, -4. And from there we use our slope idea of up 3 and over 1. In both cases, up 3 and over 1, up 3, back 1, up 3 over 1, up 3 over 1, up 3, back 1, up 3, back 1. And there we have the graph of our absolute value. Now let's go ahead and graph the line y equals -1. We remember Hoy-Vux, maybe from our middle school days, where this is a horizontal line at y is equal to -1. So we can go ahead and graph that out. And now if I asked you, where do these 2 graphs intersect? Well, we see that there are in fact 2 intersection points. They are at the points 1, -1 and 3, -1. So in terms of our x values, they intersect at the x values, x equals 1 and x equals 3. Okay, So what that means then is when we go over and we actually solve this equation algebraically, we should get answers of x is equal to 1 and x is equal to 3 because we see it on the graph. What we do algebraically should model that. So let's go ahead and work on solving this algebraically. A couple different steps that we need to make note of as we go ahead and solve. We're not just going to go ahead and isolate x like we had in the past. A couple things we need to make note of is first that we actually need to isolate the absolute value bars first in terms of solving. So we want to get the absolute value bars and everything that's inside of them on one side of the equation by itself first. So to do that, I have the option of dividing by 3 to undo this multiplication or adding 4 to undo the subtracting 4. So we're going to start by adding 4, giving us 3 times the absolute value of x minus 2 is equal to 3. Now, it's important to note we are not going to use the distributive property here. I'll say that again. We are not going to use the distributive property here. These are not parentheses we're dealing with. These are absolute value bars. So we don't want to use the distributive property. Instead, we're going to divide both sides by 3, giving us the absolute values of x minus 2 is equal to 1. Okay, so from here, this looks a lot like what we did back when you learned the idea of absolute value. We have something inside of a set of isolated absolute value bars, and we're asking you what are the values. Okay. Now, remember, our answer for this, so we were looking, when we did our answers, we always had a positive and a negative answer. Positive and a negative answer. So we're going to take this idea that you learned before and apply it to the absolute value bars. So whatever is going to end up on the inside, okay, we technically should end up with a positive and a negative value for this. So this is what step number 2 is saying. We're going to rewrite the equation as 2 equations, one with a positive answer and one with a negative answer. So we can call this the split. So a couple things to point out here. We're taking whatever value is listed there, the absolute value equal to 1, and we're saying, hey, we know that this should be equal to the positive equal to positive 1, and we're saying that this should also equal to negative 1. Again, think back to the idea of when you learned absolute value. Absolute value of 6 equaled 6, and the absolute value of negative 6 also equaled 6. So we really had these 2 answers that were vying for the possibility of being x. So taking that idea and applying it to here, we have and end up with 2 separate equations. All we're going to do now is we're just going to solve both of our equations, both for x. In this case, we're going to add 2 to both sides on the left and add 2 to both sides on the right. And we get an answer of x is equal to 3 and x is equal to 1. Now, those answers should actually look familiar. They are, because those were the x values of our points of intersection back when we approached this equation as a graphing problem, graphing the left-hand side and graphing the right-hand side and finding their intersection points. Well, when we applied the algebraic technique, we got the same x values for where they were equal to negative 1. So in terms of our solutions, we get x is equal to 3 and x is equal to 1. Now, we should check our answers here. We see that those should be the only 2 answers that we get from a graphical idea. So we've kind of checked this with a graphing approach, but just to remind you how we can check this with an algebraic approach, all we need to do is take these answers and substitute it back into our original equation and see whether we get a true statement or not, whether we get the same number on both sides. So I've substituted my answers into my original equation, and simplifying, doing the math, we get that negative 1 on the left-hand side is in fact equal to negative 1 on both of these answers. Okay, so checking it mathematically along with checking it graphically. Let's take a look at another example, another scenario that we have. We're going to solve this absolute value equation, and let's start with the graphing approach. So interpreting this one equation as a left and a right side, a left equation to graph absolute value of x plus 2 minus 5, and a right equation to graph 3x minus 1. Let's go ahead and see where, if at all, these intersect. So starting with the absolute value, we see hk of negative 2, negative 5, and slope of 1, so up 1 over 1, up 1, back 1, and so on. Now for our line, this is in fact a linear equation, but this is going to be a linear equation where we start at the y-intercept of negative 1, and we have a slope of up 3 over 1. And filling out the rest of the graph, we see our linear equation. Now, in terms of intersections, we see that it only actually intersects at one point, and that is at -1, -4, or the x value of x is equal to -1. So in terms of our algebraic approach, we should in fact only get one solution. Let's go ahead and take a look at that. Starting first, we want to not forget to isolate the absolute value bars. So drawing a line down the center of our equation, we're going to get the absolute value bars by themselves. We get absolute value of x plus 2 is equal to 3x plus 4. Okay, so at this point in our previous problem, we had it set equal to a number, and we're going to rewrite the equation. We rewrote the equation at the split as the right-hand side being positive and the right-hand side being negative. We're going to do exactly the same thing, even though there's more stuff happening here. So we're going to recopy whatever's in the absolute value of x plus 2 and x plus 2 over. But we're going to write it as equal to 3x plus 4, just normally as it is, or in this case, the positive case. And here we're going to write it as the negative case, but we're just going to put the negative in front of the entire expression 3x plus 4. So just like we put a negative in front of the 1 that was originally there, we're just going to go ahead and throw a negative in front of whatever's on the right-hand side, in this case, 3x plus 4. From here, we're going to go ahead and solve both sides. So moving variables to one side, then solving this two-step equation. Over here, we're just doing the distributive property first to get rid of that negative that's just awkwardly sitting in front. And then moving the variables to one side, solving a two-step equation, we get answers of x equals -1 and x equals -3. Well, wait a minute. How did we get two answers algebraically when graphically we know we should only get one? Well, in this case, we kind of knew this was happening. We have this little pattern that occurs over time. And that is, whenever they have an absolute value, whenever there's a variable both inside the absolute value and set equal to it, what we have happening is we have this something called an extraneous solution. That means we just have like this extra solution that doesn't actually work and is a false in terms of the inequality. Or in this case, the equation. Right? It's an extraneous solution. We only know it's an extraneous solution by checking. In this case, we checked graphically and found that there was only one solution at x is equal to -1. We could also check this algebraically by simply taking the value of -3/2 and substituting it into the equation and simplifying down and seeing whether we get the same number on both sides. Spoilers, when I plug the number in and I simplify both sides, I get -4.5 equals 3.5. This is a very false statement. These do not actually equal each other. So therefore, even substituting it in numerically, we get a false statement. Okay, we checked it both ways and we see that it doesn't work. There's only one solution. Again, we shouldn't start to recognize this. This is maybe a pattern that we want to recognize. When the variables both inside and set equal to, we're probably going to have an extraneous solution. Okay, last example. We had two solutions. We've had one solution. Well, probably makes sense that we think this next one's going to be no solutions. Let's start off with the graphical approach. Pause the video and see if you can graph this. HK -4, -2, slope of -2 over 1, and Hoivak's horizontal line here, y is equal to 4. As you can see, there are no intersection points on this graph, so it means there's no solutions. Well, what does that look like in terms of an algebraic approach? Well, let's start by isolating the absolute value bars first, and we end up with absolute value of x plus 4 is equal to -3. Now, here we have to ask ourselves, is this even possible? Remember, we're solving for x here, and x is on the inside of the absolute value bars, and we're to add 4 to it. Now, anything that falls inside the absolute value bars always spits out positive. Any number we put on the inside, we always wrote it as just equal to whatever the positive one. It never spit out as a negative value. So thinking about this here, whatever value we end up getting for x when I add 4 to it, it still will never equal a negative value. So at this point, our basic understanding of what it means to be absolute value, always write the positive answer, fails. So here we know that there is no solution. The absolute value of some number can never be equal to a negative, dating all the way back to pre-algebra. So there are 3 examples covering our 3 cases of absolute value with 2 solutions, 1 solution, and no solutions. Let's go ahead and try the practice.